Hello and welcome to another episode of Further Maths in an Empty Classroom with me, Mr. Southern. This is the first video on vector geometry, and in this video I'm going to be going through a fairly chunky example which covers a lot of the vector content that you need to be familiar with. So you can see the whole example there. If you want to pause the video and have a look at the whole thing, what I'm just going to do is go through bits of it at a time. So the first bits I'm just going to look at, we have referred to a fixed origin O. The points A and B have position vectors 5i plus 2j minus 3k and 4i plus j minus 3k respectively. So the first thing I'm going to do is it's just by preference to write these in column form. So I'm just going to write that A is the vector 5, 2, negative 3. And that B is the vector 4, 1, negative 3. And the first thing that I've been asked to do is to find a vector equation for the line AB. So in order to do that, I'm going to need two things. I need a point on the line and I need the direction vector in which the line is going. And the way that I can get the direction vector is to do the vector A to B. And the way to do that is to do vector B minus vector A, so 5, 2, negative 3, which comes out as negative 1, negative 1, 0. Now, this is what's known as the direction vector. It's a bit like the gradient of the line. And what I then need to do is a vector equation of the line is simply any point on the line. So I'm going to choose the point A, which is 5, 2, negative 3, plus a parameter or a multiplier, which in this case I'm going to use mu, and then the direction vector, negative 1, negative 1, 0. So that is the vector equation of the line through AB. Part B then, we're being asked for the magnitude of AB. So what is the length of the line from A to B? Now I already have the vector A to B as negative 1, negative 1, 0. So all I need to do to find the length of that is to crack out Pythagoras in 3 dimensions. So negative 1 squared plus negative 1 squared plus 0 squared, all square rooted. And that comes out as the square root of 2. So that is the distance A to B. Now I'm going to need this equation and this distance in the rest of the calculations that I'm going to do. So when I come on to part D later on, I'm going to start using that. But to start off with, I've got part C, which is another line which has vector equation 3i minus j plus 4k. Plus lambda 2i plus 3j minus 7k. Now what I'm just going to do is I'm just going to write that in column form, which is my preference. So 3, negative 1, 4 plus lambda 2, 3, negative 7. So lambda has been used here, which is why when I went for the vector line through AB, I used mu. So if we just remind ourselves, that was 5, 2, negative 3 plus mu, negative 1, negative 1, 0. Now in part C here, we're being asked to show that the point A lies on the line. Now this is the point A because we use that in the vector equation A to B. So I'm being asked to show that this point lies on this line. And what I need to do to be able to do that is to show that there's a consistent value of lambda for that point. So first off, I'm going to write 3 plus 2 lambda equals 5. That's setting up an equation in X. I'm then going to set up an equation in Y, which is negative 1 plus 3 lambda equals the Y coordinate here, which is 2. And I'm going to set up an equation in Z, which is 4 minus 7 lambda equals negative 3. Now, if I solve all 3 of these equations, they all have the solution lambda equals 1. and the fact that they all have the same value of lambda for x, y, and z. So therefore, the point A must lie on the line L. Right. So let's just have a think about what that tells us for a moment. What that tells us is that the point A is on this line here, the line A to B, and it's also on this line L. So the point A must be the intersection of those two lines. So I'm just going to draw that very roughly here. There's my point A, there's my point B, and this is the line L. And A is that point of intersection. That's going to come in useful a bit later on. But what I'm being asked to find in part D here is the size of the acute angle. I'm just going to underline that word acute because that's important, between the line L and the line segment AB. So on my diagram, that is this angle theta in here. Now, when I'm finding the angle between two vectors in 3 dimensions, I'm going to be using the formula cos theta equals A dot B over modulus A modulus B. And when I'm doing this with vector lines, I need to be using the direction vectors. So when I'm doing the dot product A dot B here, I need to be using the direction vector of the line L, which is this one here, and the direction vector of the line through AB, which is this one here. So the dot product multiplying the I components, 2 times by -1, multiplying the j components, which is 3 times by -1, multiplying the k components, -7 times 0, and finding the sum of those gives me the solution -5. So that's going to be the numerator of my fraction here. Now the magnitude of the vector A, if we call this one the vector A, then cracking out Pythagoras on it again, 2 squared plus 3 squared plus -7 squared is going to come out as root 62, and I'll leave that in third form because I'm going to use it in subsequent calculation. And then my modulus B, my other vector, we already know from having done this in part B of this question that the magnitude of this vector is root 2. So I'm going to be saying that cos theta is equal to the dot product, which is -5, over the product of those two moduli, I should say, root 2 times root 62. And I'm just going to use my calculator to work out the angle by doing cos inverse of that. And that comes out as theta being 116.68. Now, I just need to be aware here that I've been asked to find the acute angle here. So what's happened is this diagram, what's the calculation, rather than finding this angle here that I need for theta, it's actually found the obtuse one on the other side here. But that's not a problem. I just need to do 180 minus that answer, which comes out as 63.3. And I've been asked to give it to the nearest degree. So I'm going to state my solution for theta to be 63 degrees to the nearest degree. So key thing there, using the direction vectors of the two lines to find that angle. Okay, and the final thing that I've been asked to do then is to calculate the shortest distance from B to the line L, giving my answer to 2 significant figures. Now, let's just redraw that diagram, and I'm going to do it a little bit bigger, and I'm just going to label all the information that we've got. So we know that this point A is the point of intersection. We have the point B. We now know that this angle in between them is 63 degrees. And we're looking for the shortest distance from this point B to the line L. Now that shortest distance is going to be at right angles to the line L. Now in part B of this question, we worked out that the distance from A to B was root 2. And we're now trying to work out this distance here, which I'm going to label D. And you can probably see from this diagram that this is just a simple case of right-angled trig. So we have that sine 63 is equal to D, which is the opposite, over root 2. So therefore the shortest distance is root 2 multiplied by sine 63. Now, if I use my unrounded answer from the previous question, it comes out as 1.26. So rounded to two significant figures, it's 1.3. So two significant figures. So the key thing to being able to answer this question was to draw a diagram acknowledging that point A was the point of intersection and that the shortest distance from B to that line was going to be at right angles. And we already had all the other information we needed. We knew the length of the line, we knew the angle. Straightforward bit of right angle trig. Job done.